Hello, and welcome to Acoustics Derivation. In the previous video, we looked at and derived reflection and transmission coefficients for a wave impinging on an interface between two fluids at an oblique angle. We considered this diagram on the left. We had an incident wave and an interface at x equals 0, a reflected wave, and a transmitted wave. Medium one had fluid or parameters rho one, C1, so density and speed of sound, and medium two had rho two, C2. When we were doing that derivation, we derived we derived the law of specular reflection, which stated that the angle at which the incident wave comes in is the angle at which the reflected wave goes out. We also derived Snell's law, which says that sine of the incident angle divided by the speed of sound in medium one is equal to sine of the transmitted angle divided by the speed of sound in the second medium. And then we derived these two equations here, or expressions here, for the reflection coefficient R and the transmission coefficient T. So if you are not familiar with that derivation, I encourage you to go and check out that video before you watch this one. Why? Well, today we're going to be looking at a few special cases that can come up in this problem. So the first one is known as perfect transmission. So if the incident wave is fully transmitted into the second medium, we call that perfect transmission. So there's nothing reflected. In other words, capital R, the reflection coefficient, is 0. The way that this can occur is, if you're taking a look at this expression, is that rho 2 C2 cosine theta I is equal to rho 1 C1 cosine theta T. Now, we call something, or we've named something called the angle of intromission, which is the angle at which all the sound is actually transmitted into that second medium. So in other words, we will define theta I, where R is 0, to be the angle of intromission. We'll call that theta naught. And again, that's the angle at which all the sound is transmitted into the second medium. So using Snell's law, one can actually calculate the angle of intromission, and you obtain the following expression. Sine squared theta naught is equal to Z2 over Z1 squared minus 1 over Z2 divided by Z1 squared minus C2 over C1 squared. What you might be asking is Z2 and Z1. Well, that's the characteristic impedance of the medium. Simply rho C for each medium. Rho 1 C1, rho 2 C2. If you so choose, you can rewrite this expression in this way as well. Just like that. So it's important to note that not every pair of media has such an angle. So it doesn't necessarily have an angle of intromission. So the next special case is grazing incidence, which we'll say is when the incident angle is 90 degrees. If this is the case, then R becomes negative Z1 cosine theta T over Z1 cosine theta T which is equal to -1. And we also find, if you recall, that 1 plus r is t, that t is equal to 0. So we see that even if the difference in impedances, Z2 over Z1, is large, it turns out that at grazing incidence, medium 2 actually behaves as though it were some sort of a pressure release material rather than the material that it is. So you could think as you start approaching more and more, uh, coming in more and more close to the vertical axis here, it seems that the second medium becomes more and more like a pressure release material. Another way to think about it is that the acoustic impedance of the second medium appears to be getting smaller and smaller as you approach 90 degrees compared to the acoustic impedance of the first medium. The last and arguably most interesting special case we can look at is total internal reflection. Which leads us into a critical angle, and we'll define what this is in a moment, as well as an evanescent wave. So let's consider total internal reflection. We begin by looking at Snell's law, and we recall, if we manipulate it a little bit from above, that the sine of the transmitted angle is C2 over C1, so the ratio of sound speeds times the sine of the incident angle. Well, you can solve for the transmitted angle by simply taking an arc sine of both sides. So we have that it's the arc sine of C2 over C1 times sine of theta I. And this turns out to be real if and only if, so it's real if and only if C2 over C1 times sine of theta I is less than or equal to 1. If you just think back to your trigonometry days or your pre-calculus days, the argument of the arc sine must be less than or equal to 1. So when the value of theta I leads to C2 over C1 sine theta I being equal to 1, we call that the critical angle. And so we can define the critical angle theta CR as the arc sine of C1 over C2. So that'll tell us what theta value makes C2 over C1 sine theta I equal to 1. Now, why is this important? Well, at critical incidence, the transmitted wave travels parallel to the interface, i.e. it travels at 90 degrees. So if we go up here again and we change color, you can think of an incident wave coming in like this, and then at critical incidence or at a critical angle, the wave in the second medium goes right along the interface. So we'll call this critical angle. So what actually happens is if you go beyond the critical incidence such that theta I is greater than theta critical, the transmitted wave cannot emerge at any real angle. So it turns out that the result is something known as total internal reflection. That is, no real wave can get into medium 2. Well, why is that important? Well, let's consider some time harmonic waves. Oops, let me go back to that. So let's consider some time harmonic waves. Namely, the three that we considered before in the derivation to get R and T. So I've written out here the three time harmonic functions we considered when we were deriving the reflection and transmission coefficients in the previous video. So then we can begin to manipulate these these equations here by first noting what I've written here, that theta I is equal to theta r, as we showed previously for the law of specular reflection. We can also change this component or this portion of the exponent by recalling Snell's law. Scroll up. Snell's law, and noting that we're at a constant frequency. So it turns out then that negative k2y sine theta t is equal to negative k1y sine theta I. It turns out that sine theta I is real for theta I is greater than theta critical, and thus sine of theta t is real for theta I greater than sine of theta critical. But take note of this portion of the transmitted wave. Cosine theta t is equal to, from your law of the Pythagorean identity, I should say, sine squared plus cosine squared is equal to 1. So we can write that as 1 minus sine squared theta t. If we invoke Snell's law again, we can write this as plus or minus 1 minus C2 over C1 squared sine squared theta I. This is by Snell's law. Now that we've written the expression like this, we note that above critical incidence, we recall that C2 over C1 squared times sine squared theta I, or rather C2 over C1 sine theta I, is greater than 1 above critical incidence. But that would give us a negative under the square root. So we can take the imaginary number out and rewrite the square root as C2 over C1 squared sine squared theta I minus 1. This is when theta I is greater than theta critical. Well, that's interesting. Let's just pause for a second. So we had our time harmonic waves, our incident wave or reflected wave, and our transmitted wave. And we see that in the x component of the transmitted wave is, if the incident wave is above the critical angle, that's going to have an imaginary times an imaginary. So this exponent is going to be real. Well, what does that mean? Well, we'll get to it in just a moment. For simplicity with our writing, let's gonna let b be equal to, we're gonna let b be equal to the square root of c squared over c2 over c1 squared sine squared theta I minus 1, and this is real and positive. Thus, we see that if theta I is greater than theta critical, cosine theta t can be equal, or as written as plus or minus jb. So it actually turns out that physics dictates that we must choose the minus j rather than the plus j solution. Why? Well, the minus sign will lead to an exponentially decreasing amplitude in the wave rather than an exponentially growing signal. In other words, the minus sign is so that the transmitted pressure wave is bounded as x goes to infinity. So we're gonna write this as cosine theta t is equal to negative jb. Thus, we can, let me write that a little bit cleaner, negative jb. Thus, we can rewrite our pressure expression, plugging in our new expression for cosine jb, and we'll figure out then what this means that it's a real part or real component of the exponential rather than imaginary. So we see then, if by plugging that in, that PT is equal to AT times e to the negative K2 BX times e to the j omega, excuse me, got the parenthesis, e to the j omega t minus k1y sine theta I. So now that we've written in this form, we're gonna let alpha, and maybe you've seen this before, help us simplify this complex exponential. So alpha is equal to K2 times, and then I'm going to rewrite B, just so it's a little bit clearer, C2 over C1 squared sine theta I minus 1, oops, sine squared theta I minus 1, such that we can write PT is equal to AT e to the negative alpha x times e to the j omega t minus k1y sine theta I. This is called an evanescent wave, i.e., not a true wave. Although we can see that there's a time varying signal and this evanescent wave moves along the interface as defined by or described by this term, it does not propagate into the second medium. Rather, the amplitude decays via this exponential term, e to the negative alpha x. Interesting to note about evanescent waves is if the incident wave is removed, the evanescent wave instantly stops. Also, the penetration depth is proportional to the wavelength in the second medium. Furthermore, the higher the frequency, the more poorly the evanescent wave penetrates into medium 2. So when we write it in this form, you can see that there's no time harmonic propagation into the second medium because there's no j, so there's no imaginary. So this, like I said, is just an exponential decay. Now, let's assume that our second medium is actually a finite thickness. So we have our medium 1, medium 2, and then medium 1 again. And let me draw a horizontal line here. Okay, so let's suppose we have our incident wave impinging here at some theta I. This is our incident wave. And let's let theta I be greater than theta critical. So if we have this incident wave impinging on the interface at some theta I greater than theta critical, you can kind of look at the evanescent wave field or the evanescent disturbance, which looks like an exponential decay in the second medium. But there's a non-zero amplitude if the second medium has finite thickness. Or I should say non-zero, non-zero amplitude thickness. Well, it turns out, and I'm going to read this directly from David Blackstock's book on fundamentals of physical acoustics because I think he wrote this very, very well. So it turns out that if medium 2 is finite in extent beyond which medium 1 exists, like we've drawn here, it turns out that the evanescent wave is reflected from the second medium or the second interface. The reflection is in turn reflected from the first interface and so on. This bouncing back and forth of the evanescent waves, albeit with exponentially decreasing amplitude, actually sets up a standing evanescent field inside the second medium. The time varying signal at the second interface travels along the interface with the same trace velocity as the first interface. What does that mean? Well, although the diminished amplitude at the second interface, or is at the second interface, this excitation radiates a true wave, so not an evanescent wave, into the second medium or the second section of the second medium. It also turns out then that this transmitted wave actually has the same angle as the incident wave because the trace velocities at each of the interfaces are the same. So because the trace velocity at the second interface is equal to the trace velocity at the first interface, it launches a real wave in this in the second medium one with the same angle. So as I bring this video to a close, we looked at three special cases for reflection and transmission at oblique angles. The first was perfect transmission, where we said that R was equal to 0. The second was grazing incidence, where theta incident was equal to 90 degrees. And finally, and most importantly, we talked about total internal reflection and found our critical angle, and that let us describe an evanescent wave in a medium. So this concludes this video. Thank you.